Hello everyone, I'm Zach.
And I'm Owen.
I'm gonna introduce our final project, the traffic sign recognition.
The main objectives of this project are to pre-process the images and to train a model, test a model, and implement live classification. The main goal of this project is to mimic the fundamental algorithm of self-driving vehicles. The dataset we're using is the German traffic sign recognition benchmark, or the GTSRB, which is freely accessible on the internet.
In general, the dataset includes 43 classes and 50,000 images. The dataset has already been split into training set and testing set. For training set, there are 40,000, and for testing set, there are 10,000. We do some pre-processing in the dataset. First, we resize the images. As you can see from the left-hand side graph, uh, not all the images have the same size. So we resize them to the 32 by 32. It is super convenient to run the model in a convolutional neural network with this square resolution. Then we do some data augmentation. As you can see from the right hand side graph, there are different image counts for different class. So the data is unbalanced. The model might overfit the classes with more data. Therefore, we did some data augmentation. First, we do some horizontal flip. It is a good way to augment the symmetric images. There are some example in the right hand side. As you can see, after flipping, the image's content remains the same. Then we do some rotation. Some rotations at a small angle is really good. We do some randomly rotation between -10 and 10 degrees. As you can see, there are some example, and the main content still remains the same. Finally, we do some other methods, like adding Gaussian noise or adjusting the brightness. As you can see from the right hand side graph, after augmentation, they are totally roughly equally distributed classes image, so it's great for running the model. Next, let's Owen to introduce our recognition model.
Thank you, Zach. The recognition model we're using is based on the convolutional neural networks and PyTorch. It is very similar to what we did in machine learning homeworks this semester. And in the codes, you can see that there are two convolutional layers with two max pol layers and two fully connected layers in the end. In the beginning, what we did was that we had three convolutional layers and three max pol layers and four fully connected layers in the end. But after we cut off actually a large portion of the layers, it reduced much in calculations, but it still gave out pretty impressive results. But there was a flawed attempt in the first. On the left is a log of the first training that we did. As you can see, the training accuracy right here is 0.034. But throughout the epochs, the accuracy doesn't rise up much. And what is worse is that the training accuracy actually falls to zero randomly sometimes. And the training loss is dropping slowly, which are both not expected. We found out the problem was that um, many of our training images are in a sequence. That is, a same class has thousands of images of the same type. For example, on the left, these images are all the same, and they are at once feed into the model together. Uh, so what results from this is that the model is trained to fit many images of one class, but not images of other classes, which is bad for learning. So when the model takes in another, say, 1,000 images of another class, it doesn't recognize them, and the training accuracy will be zero. We solve this problem by shuffling the images after pre-processing, so the images are all randomly fitted into the model. And after shuffling, the training results are as follows, which are quite impressive actually. The validation results, validation accuracy and testing accuracy are both above 80%, which is very good. And after training the model, we started to use the model. Because training the model takes up very long time, we actually save the model after the training so that we don't have to spend all that time when we're using it. On the upper picture is the code for saving all the weights, and on the left, on the bottom picture is the live test function where we initialize the convolutional network when we wanted to use it, and then we load all the weights we had saved before. And right now, we're about to show you a video of the live test with live camera, and the model's prediction. Right now what you're seeing is our code for the live testing function. As I run this, there will be two CV2 windows. The one on the left is the camera of my laptop, and the one on the right is what the program is predicting. As you can see, it is not accurate all the time, but let me proceed to show you the demo. Because I had set the refresh rate of the function to be once every second, what you see here is every second the camera takes in the frame and fit it into the model and get the output probability.
Our model has several advantages. It is pretty accurate. Also, it can recognize images on a real-time basis. However, so far our model doesn't support traffic sign detection. So possible improvement may include implementing lab detection algorithm that doesn't require the user to point the camera at the sign.
And these are the references we had during the project. I wish you all drive safely, and thank you.
Thank you.